All right, hello everybody. Welcome to EEE 135. This is Professor Dr. Trey Stoops. Here we're going to learn about renewable energy systems. Specifically, we're going to start chapter 3, which is solar photovoltaics. So this is the introduction to the solar energy resource chapters. Before we get into any more details, we have to learn exactly how the individual solar panel works, kind of the physics behind it, where the electrons go, that type of stuff. Then we can start building a bigger system, and eventually get to like the solar arrays that we see on people's households. Okay. So very first thing we need to talk about is semiconductor materials. So PV system is at the end of the day kind of an electronic device and is made by silicon. So the major material used in any semiconductor is silicon. Silicon is one of the most common elements in the earth. It's everywhere, and all we have to do is just take it, melt it, and reshape it, and then you could get whatever form you want. Okay. Silicon is very, very important for electrical engineering because this is material that made any microprocessor, any transistor level device possible. We've been using this in the 1950s. Every computer, every cell phone, everything's made out of silicon in today's world. Okay. So if you took electronics before or taking it now, you're probably going to hear about silicon as well, right? A lot of diodes, transistors, other devices are made from that material. Okay. So silicon itself is an element which has 14 protons and between 14 and 16 neutrons. It kind of varies a little bit, right? And 14 electrons. So a quick review on chemistry and the atomic model is you have a nucleus in the middle for silicon. It has 14 protons. We'll have 14 electrons and valence shells around it, where the first valence shell will always have 2 electrons to meet its criteria. The second ring will have 8, and then the third ring will try to have 8 as well. So naturally, they want to go to 2, 8, and 8. Okay. So the outer shell for this silicon atom wants to have 4 valence electrons, but if you do the math from 14, we're missing some. So we only have 4 out of the 8. So anytime you have another molecule that comes nearby, they're going to bond together to share the outer electrons, and they'll share within each other's outer shell. So here, this is why you'll have metals and silicon, which will naturally form together to make clumps, and then that's that hard surface you're talking about. So if you see right here, you have 5 silicon atoms, and you can see the middle one has all 8 electrons because it's sharing one from each of its neighbors. So every silicon will end up having 4 molecules nearby, making a nice little perfect square shape, right? Think about this over and over. You can get this nice perfect grid, the lattice structure, and that's why we have metal things and solid objects. They tend to be very structured and have a very clean lattice structure. That's why they're smooth. Okay, so main thing to take away here is there's valence electrons. We have 4, and we want to get to 8. And then when we have silicon on its own, it's just going to make a giant bed of them, and then everything's going to be stable. And this is a very stable and sealed element. Okay, now silicon alone doesn't really help us because we actually, as electrical engineers, we actually want electrons to flow, not to be stuck in the atom. So when electrons flow, that's when we have current. And when current flows with voltage present, you're going to have power generation, and power gets delivered to the load. So we can't have our electrons stuck. We need to make some float around a little bit. Okay? This is what a wire is. A wire is a piece of metal that has electrons floating between the atoms freely or very easily. That way, atoms will knock around everywhere. Okay, plastics is a very strong dielectric because all the electrons are very squished into the atoms. It's very hard to knock, very, very hard to knock electron out of its valence shell and conduct. So this is why it's called semiconductors. So this device does not conduct normally, but we could kind of halfway conduct. That's the semi part. So how can we get a silicon sheet of atoms to conduct, right? Well, silicon on its own is not really that good of a conductor because atoms are all linked up together. So what we can do is we could create an excess amount of electrons or a deficiency of electrons. And one way we could do that is we could introduce different elements into the lattice structure, right? So for example, we can add what we call impurities to the crystalline structure of silicon, right? One thing we could do is we could put antimony, which is another element. This is element atomic weight 15 because it's one more than 14 that has an extra electrons. So in the lattice structure, we could put a molecule of antimony here, an atom, and then remember it wants 8 electrons in the outer shell. Antimony has 5 electrons normally, and the surrounding 4 atoms give it 4, so it ends up having 9 total, right? Which is too many. So we actually have 1 free electron that gets popped out of the antimony atom, and it kind of floats around a little bit. So by doing this, we actually have a free electron floating in the areas between the molecules, and that is an electron we can use to move and charge and go do work. Okay. The opposite to that is we can devoid an electron from the shell by using boron. Boron is element 13, so it actually only has 3 electrons on its outer shell. So when we have 4 of the silicon nearby, that's 4 atoms from them. Boron has 3, so we have 7. So we're actually missing 1. So we can have this, we call it a hole, because there's an extra point where an electron wants to come in, but we're just naturally missing it. Okay. And the idea is if we put these two close together, this free electron is going to want to eventually move over and fill this boron atom, this hole right here. And anytime you can force an electron to move across a distance, you can exert energy from it. And that's power. That's at the end of the day, that's what power generation is. Any electric generator is take electrons and slinging them somewhere else. Okay. So the big point here is with silicon, we could put extra, or we could replace some of the atoms with different types of atoms to create these extra electrons or these extra holes or voids. And this is where we could start really using this material for semiconductor to electrical engineering. Okay, this technique is called semiconductor doping. So doping is a process of literally putting in an impurity into the lattice structure to get the free electron. Okay, now we know we have a group of silicon that has extra electrons and another group of silicon that is missing one. So we have 2 separate types of materials. Okay, we could call this a p-type of material because p-type has a deficiency of electrons. I like to think of p as in proton. It has an extra, a positive charge. So there's a net extra, is missing electron, but missing electron is like we have an extra positive charge. We need to fill that in with the electron to neutral to make the atom be electrically neutral. N-type has an excess of electrons, so N, think of a negative type of material. It has too many electrons. It has a net negative charge. It needs to get rid of the electron to be electrically neutral. Okay. And what really smart people did in the 1950s and 60s, they figured out that if you make these 2 materials, an N region and a P region together, on the border here, the extra electrons will then travel over and fill in the holes of the p-type region. So there'll be a border in between the N and P region called the depletion zone, where it's all electrically neutral, all the electron kind of filled in, and then everything's fine. So here, if we join 2 materials together, the border the free electrons will fall into the holes, completing an 8-electron band. This creates an electrically neutral barrier. So it's a very small barrier, which kind of helps because we don't want all the electrons to fall over. Once this is electrically neutral, it's harder for this electron to kind of go through the depletion zone to the P region. There's going to eventually be a barrier that it's harder for it to climb over. Okay, so at this point, we have a bunch of free electrons and a bunch of holes. This is kind of a battery now, right? We have a difference in polarity, a difference in charge. There is a voltage across its depletion zone. It's about 0.7 volts is typically what you measure. And then that we could put a resistor or something else and create some electricity. Okay. So that's kind of the idea of a PN junction. Okay. Now, how does it turn into a perpetual energy machine forever, right? That's the next big question. So, kind of by accident, they realized if you take this silicon and put it in sunlight, it actually perpetually makes like a little bit of electricity, right? So they call it photovoltaic. PN cells are PN junctions slapped together with a middle depletion zone. You put it out in the sunlight, right? The sun rays come to the earth. A sun ray is literally a single proton getting shot like a bullet towards us. Okay, so what ends up happening is you have sunlight falling into the N-type region. Remember, the N-types, they have extra electrons floating around. Okay, so the sun photons will fly in, kind of like playing pool. If you're lucky, it'll literally strike an electron and shoot it out. It'll pluck it out of the material, and then it'll start moving and it'll find its way outside the material, right? If you give it a path to leave. So sunlight comes in, knocks out electrons. Remember I said anytime you have electrons moving, you can make power out of this. Okay. So as a free electron leaves, it travels to the load and returns to the p-type material. So all we have to do now is we have the sunlight hitting the n-type material with extra electrons. It's going to start wanting to move. Let's take a wire, give it a path to leave the n-type material, and let it go through the load. So now we have a bunch of electrons that want to get out. They're going to go through the wire to the load, which let's say it's an LED light. A very small LED light. It's shining up the room. It'll go through the load and it'll come back into the p-type material. So now the extra electrons will come over here. It'll settle in a hole, but eventually it's going to wander over and come back through the depletion zone. Because eventually we're going to run out of electrons here and it's going to want to pull more electrons through the depletion zone. So electrons will flow out to the load, come back into p-type material. It'll take a while, but it'll eventually kind of waver its way through the different holes back to the n-type material. And this is a perpetual machine where the electrons will always keep flowing as long as sunlight is present. Okay, the sunlight is a key part in knocking the electron and making it all start. If there's no sunlight, everything stays still and nothing happens. Okay, so it's kind of fill out the text. As a free electron leaves, it travels to the load, returns to p-type material. Then the electron will travel through the p-type. So the electron passes through the depletion zone, which is the middle area, back in the n-type material. And in bold, remember in circuit 1, completing a full path electron induces current in the circuit. Okay, so as long as the electron can leave and come back in and do this over and over, there will be current flowing, and now we got to produce power. That's the whole reason why we're talking about today is we want to make power out of sunlight. So that's the innards of how a PV cell works. Okay. Here's kind of a more realistic, like physical version of what it will look like, if you can imagine it. The very top region right here, this is the N-type region, right? We put a nice little conductive grid on it. So if you ever look at a PV panel, you see little lines everywhere. The more lines we put in, the easier it is for the electron to hit a metal wire and then conduct faster. The electron will always travel faster over a metal wire than through the lattice structure of the n-type material, right? Because it's not metal to begin with. Okay, so we want to put very thin, tiny little lines here. That way electrons have an easy path to get on and get on the main metal bar and then leave to the load. We don't want to put too many wires here because every wire we put in blocks the sun. So it's a kind of very, I'll say maybe I only want 5% of my surface to be wires. If I'd say 50%, yes, the electrons will get out quickly, but you're going to block all the sunlight. You're going to shoot yourself in the foot. Okay, so very thin little wires, no more than, let's say, 5% of the surface, to help the electrons leave. Okay, at the bottom of the whole cell is a metal conductive layer. So this is literally a metal sheet that when the electron flow back into the sheet, it'll flow anywhere in the sheet and then go back into the p-type material to then return back to the PV cell. And that's a continual electron movement process. Okay, so think of this like a giant pinwheel that's just slinging electrons all day long into the load. Okay. A lot of times they like to add an anti-reflective coating on top of the silicon and the wires to make sure the light doesn't bounce off. So remember, if you have a lot of a reflection, that means that the light comes in and it bounces off. We don't want that. We want all the light to penetrate into the PV cell. We don't want any reflection, right? So if you ever look at a PV cell, it should never be a mirror. If you can see yourself, then that means something's wrong, right? It's reflecting too much sunlight. So there's anti-reflective coating to make sure that the sun rays go into the PV panel and they don't bounce off. Okay, so that's pretty much how a PV cell, the physics behind a PV cell, how's it work? Okay, so here you can see like these little squares. These are individual PV cells, right? And now we can start. Now we can start talking about a little bit of the material science behind it. So we know electrically what's happening. We know chemically what from an atom level what's happening. Let's talking about how to build them. There's three major types of PV cell structures from a material standpoint. One is called monocrystalline cell. This is where we took the silicon, we melted it into a giant bar, and we sliced off little pieces like a sliced bread loaf. And that little loaf of bread, that silicon, it's one complete structure. There's no cracks. It's perfect. It's perfectly smooth. That's the mono part. So it's a solid silicon structure, crystal. Efficiency of this is about 15 to 20%. And this is about the best you're going to get. Unfortunately, when the sunlight hits, not every sun ray hits a photon. I mean, not every sun photon hits an electron. There's a very high miss rate. So unfortunately, you've got 1 in 5 chance at best. Okay, but anytime you have a solid silicon, it's the easiest for the sunlight to penetrate. There's no cracks. There's no things that can deflect it. It's nice and smooth. That's the best you're going to get. It's also the most expensive. Why? Because it's the hardest to process, right? You have to make sure that each piece is flawless. If you have any breaks, you have to throw it away. Okay. Polycrystalline cells is kind of the next level, where instead of having one solid piece, you have a bunch of broken pieces you could glue together. So think about taking a bunch of glass that's shattered. We could re-glue them together to kind of half make the mirror again, or make a glass that's kind of with cracks everywhere. It's better than nothing, but that's pretty much what the poly part means. So it's basically all these extra shards that failed in the monocrystalline process. We glue them together, and then we can still have a PV cell, but it's just not going to be as efficient because, you know, if you take a 6x6 square polycrystalline, they're going to have little gaps everywhere because you can't perfectly put all the pieces together, right? So a little less efficiency. You're talking about 13 to 16%, right? It is definitely one of the cheapest ones because you're using waste product to rebuild to another product, right? But I wouldn't personally use this. I'd pay the money to go monocrystalline, but if you got to be cheap, you don't care about efficiency as much, the polycrystalline works as well. The last one is thin film. So the first two, they're pretty solid, meaning you can't bend them. If you bend them, they shatter and break. Okay, if you try to bend plastic, eventually cracks. Same thing here. The third one, thin film, this is actually kind of wavy. So think of like a very thick, it's not aluminum foil. It's thicker than aluminum foil, but think of it like wrapping paper, I guess, where you could mold it around an object. That's the whole reason why people like it. So if you have a curved object, you could kind of glue the thin film across it for like a circular or semicircular area, right? So it's very flexible. It's very easy to apply, right? It's lightweight. So people think it's awesome. It's like this flexible ribbon of silicon, but it comes at a cost. The efficiency. It's the lowest of all of them. We're talking about 9 to 11%. One of the main reasons why is too thin, right? The thicker it is, the more electrons that flow within the width, the better the chance the sunlight has to hit one of the electrons. So by making it really thin and flexible, you're lessening the amount of electrons in the surface area that the sun hits. So it's a give or take, right? If you can't handle solid flat planes, like you have to put it on a curved object, you kind of have to use thin film. Okay. So it's cheaper, but it's not the cheapest. So it's kind of middle ground in terms of cost. Again, monocrystalline is probably the best one. That's what most people use, but others are there in case you have some unique reason why you can't. Okay. Now that's on the physical construction. In terms of the main material to build a PV cell, we've traditionally always used crystallized silicon. The most common type silicon literally comes from sand that you just melt into silicon. I mean, when we have way more sand than we ever need to do in this earth. It is the best price versus performance if you want for long-term viability. There are other materials we now research can do similar properties. Another one's called gallium arsenide, GaAs. This is an experimental alternative silicon. It's higher efficiency, it's very heat resistant, so it's a superior version of silicon. But like all things electrical engineering, it's expensive, meaning it's kind of a no-go, right? Would you rather spend $200 or $400 for a solar panel, right? Obviously, I would choose $200. Even if the efficiency is maybe 10% more, it's not worth the cost. So that's the problem with those go-to. Other other separate things you're trying to look at, there's a dye sensitive solar cell. So the logic is instead of having a solid piece of structure like a lattice structure, we can literally have liquid electrolytes. So instead of the silicon lattice structure, it's more of a fluid type of liquid where you have the molecules moving around. Some of the molecules have extra electrons. So it's just like a kind of like water flowing around where the sunlight hits it and knocks electrons out. Okay. Obviously, the water and whatever you put in is pretty cheap, right? It's very simple in that the process is you just fill it, you just fill a glass tank with water and you put this special liquid electrolyte and there you have your solar panel. So people are like, oh, this sounds really good, right? Here's the biggest problem is very low efficiency, like way worse than the other two. You barely get any of my energy out, and main reason why is because liquid moves too much, right? You're not going to be able to get anything stable when it's going all over the place. Number two is high maintenance. Anytime you have liquid, you have leaks, you're going to constantly look at it and refill it. It's going to evaporate. So it's a lot of headaches. Cool on paper, but commercially not viable yet. But in the future, it might be. Okay. So just different types of material we can use. Somebody else got really smart and said, well, thin film kind of sucks because it's too thin. Well, what happens when we put multiple layers on top of it, right? And we can, right? So all we got to do is make sure that we have a translucent thin film on top, and we could put maybe 3 of them together. So you can see right here, we have 1, 2, 3 cells. Now, why do we want 3 cells? Well, each type of material can only take a certain band of the light spectrum and take energy from that. It's not the whole entire spectrum. So what we can do is we can cover more of the light spectrum by having multiple PV junctions with different wavelengths to capture. And we'll put it on top of each other like a giant club sandwich. That way the sun ray that hits can go through 3 layers of PV panels and each one take a certain level of the wavelength. Remember, the sunlight hitting the PV panel, it has all wavelengths, not just a very specific one. Okay, so by adding more layers, we can increase the efficiency of thin film, more chances for a photon of varying wavelengths to knock out free electrons. Okay, kind of a good image to show you what's going on. So think about you have all the sunlight coming in. The cell 1 has a high band gap, so it's going to take the visible spectrum and all the wavelengths here, right? So the very small, tiny wavelengths, very tiny, fast frequency wave sunlight is going to get absorbed by the first cell. The bigger ones will then penetrate through and go to the next cell. And cell 2, you can see, captures that middle bandwidth. And the last cell will capture the larger ones. So in definition, here you're just getting more sunlight absorbed than just one layer. Okay. So I mean, it sounds like a good idea. I think it's quite expensive to have 3 different materials to glue them all together, but I'm on board with this. If we could make it cheap enough, be viable, sure, why not? Okay, give me 1 second. So That's all the physics behind it, the chemistry, blah, blah, blah. Now let's start talking about the actual circuits and the raw electrical engineering part. So when you go buy a PV cell, right, you typically buy it as a bunch in a panel, but a typical PV cell is a 6-inch by 6-inch wafer. So literally about this big, right? Here is your silicon with all your doping and p-n junctions all built into this. So you're just going to see this image. Okay. Electrically, how can we use this to build circuits? You can typically assume that a standard PV cell produces 0.5 volts DC and 2 amps DC coming out. So a single cell, given ideal sunlight, will produce half a volt out of its terminals with 2 amps flowing out to the load. Okay, so power-wise, how much power is going to produce? Well, a single cell is P equals V times I, so it's going to be 1 watt. So one cell is 1 watt. That's how you have to think about it. Right? Now, 1 watt's not a lot. You can't really do much, so we have to put them together. We typically put a bunch of them in series or in parallel to start building up the power. So the question is do you put them in series or parallel? This starts becoming a design issue problem. Okay. Typically, first thing you want to do is you got to ask yourself how many of these you want to put in series. Why do you want to put PV cells in series? Right? Well, you can increase the output voltage. So we can place many PV cells in series, and this is called a PV string. Right? Every time we add more, we're going to increase the voltage. Because remember, things in series add up voltage. Okay, now because it's in series, it's going to share the same current throughout. So the current is going to stay the same. It's not going to increase. So remember, everything in series, current stays the same, voltage increases. So we have 6 of these in series. What's the total voltage of a PV string right here? Well, we have 6 cells at 0.5 volts each. So we're going to get net total right here of 3 volts. So this load is going to see 3 volts. The current, because they're in series, stays the same, so it's going to be 2 amps. So this load right here is seeing 3 volts at 2 amps. So what's the total power of this system we have so far? P equals V times I, we got a net 3 volts, the same 2 amps. We're going to get 6 watts, which makes sense because we have 6 PV cells, and each one produces 1 watt in general. Okay, so you can put as many of these in series to keep building up the voltage. You can get 48 volts, 72 volts, 100 volts, right? You're just adding a bunch of them in series, and that's typically what we do. Okay. Now, this is neat to increase the voltage, but what about increasing the current? Well, another thing we could do is put them in parallel. So typically, design-wise, step number 1, ask yourself how many of them do you want in series to create a respectable voltage. One of the starting design process is always what voltage do I want my system to be? Do I want 12 volts, 24 volts, 36, 48? Okay. So let's say I want 12 volts, start putting them in series until you reach 12 volts. Okay. And then the step 2 will be, well, how much current do we want? Well, it depends how much power we want. We have the voltage set. Now we start increasing the current. Okay. How do we increase the current? You want to put things in parallel. Parallel circuits, the output voltage always stays the same, but the current will increase. So let's say we have our 6 cells already. We know the top half right here, this is 3 volts at 2 amps. So let's say I put 2 sets in parallel. So we have a 6 cell string in parallel with another 6 cell string. Right? What's the voltage of this whole setup? Now remember they're in parallel, the voltage stays the same. It's still that 6 cells times 0.5 volts. So this wire right here, both points right here, and up to the load, all is 3 volts. But notice this node, we have 3 wires coming through. So we have 2 amps flowing from the first string. We have another 2 amps flowing, so they're going to double up. Because remember, with a node, we add up how much current is flowing in, and that goes out to the load. So we have 2 amps here and 2 amps there. We add up to 4 amps. So now, what's the total power of this resistor here? This load has 3 volts at 4 amps. So P equals V times I, 3 times 4 is 12 watts. So you can see we have a building block system now. We take an individual cell, we start stacking them up in series to get the voltage. Once we get the voltage, we could copy and paste that string over and over again to increase the current. Now, one of the big no-no in all this is you cannot put two PV cells with different voltages in parallel. So this is 6, and another one we have is 10. You cannot link them together. It's something we should learn in engineering 17 is the only time you put things in parallel, they have to have the same voltage rating. Okay, so you can't mix and match different size PV's strings. They all have to be the same. Okay, so that's how you put them in series and parallel. Let's give you an example to see everything pan out. Right. So given we have a single PV cell, we have a manufacturer that gives us PV cells. We have as many as we want. That we know the output is 0.5 volts. It has 2 amps and has 1 watt power output. I want to design a PV module, right? Think about something the size of a dining table. We're going to put a bunch of them to create this giant rectangle, and that's going to be our PV module. Okay, you typically buy these from Amazon for like $300-400. I want my output voltage to be 24 volts out of the whole system, and I want to make sure I have 96 watts. All right, so let's start working. So step number 1, we always look at the voltage source first. I know I need 24 volts right here. I have 0.5 volts per, so my total voltage of the system is always be 0.5 volts times the number of cells in series. Well, I have 24 volts right here. I know I have 0.5 volts per, and as a number of cells, we just do some basic arithmetic. I need 48 cells in series. So I'm going to take 48 cells, string them up in series. It's just connections, right? And then I can eventually get 24 volts. So my design so far, my PV string is 24 volts. PV string requires 48 PV cells in series. Okay. Now, we have our string set up. Let's make sure we could get enough power out of it. Okay. I know I have 48 cells. Each one's 1 watt, so 48 watts. So I don't have enough power yet. I need to add more. Right. So the total power is 96 watts. I know my string power is 48 watts. And I need to multiply by n to figure out how many of these strings I need in parallel. Remember, we copied the string. Once we have the string, we copy that design. We just keep pasting it over and over again until we get the correct power output. Right? The numbers kind of pan out nice and easily. We just need 2. So then we just order another 48 cells, put them in series, and now we have 2 48 cells in series, like here, and we join the negative terminal together, we join a positive terminal together, so now these 48 cell strings are in parallel. And so how many did we use in total? We used 96 total cells. I call it a 48 by 2 setup. 48 in series, 2 of them in parallel. Okay. You will have a time that maybe these numbers don't always work out correctly. So you're going to have to over-design maybe a little bit. And just because if I said 120 watts, you cannot just say, I want 2.6. Right? You have to go all the way to 3 and just be a little bit larger, which is fine. It's a little wasteful, but you can't really do anything about it. Okay? So that's kind of just a little example to show you. Here, I want to go ahead and take our 15-minute break. I want you to do an exercise. We're going to do the same thing, and you're going to figure out on your own build a PV or design a PV module. So here, given we have a PV cell that outputs 5 volts at 2 amps for a 1 watt output, standard PV cells, right? I want you to design a PV module that has a 48 volt output, right, of 96 watts. So previously we had 24 volts. I want you to change it to 48. So you tell me what happens. So number 1, design the PV string to meet 48 volts. Once you have that, go to step 2. How many of these are needed in parallel to meet 96 watts? How many cells do you use in total? Do this same, very similar to what we did before. Okay. All right. So good luck with that. Come back in about 15 minutes or so, and we'll see how you did and check your answers. So, see you in a little bit. All right. Hello, everybody. Welcome back to EEE 135, Chapter 3, Solar Voltaics. Here, we took our 15-minute break. We came back, and let's check out this exercise. So remember, it's about building a solar module. So let's go ahead and see how we did. All right. So difference here is we want 48 volt string instead of 24. So we have 48 volts is equal to 0.5 volts per cell times the number of cells. So just do some basic math. We need 96 PV cells in series. So we're going to have a very large, big, one very, very large, big, long PV string of 96 cells. Okay. So still want to keep the same 96 watt power output. So we would do here. So we know PV string is 96 cells. Each string is already 96 watts. So honestly, at this point, you don't need a second one, right? One cell gives one PV string gives 96 watts. That's all we needed. So we basically nothing extra in parallel. So we only need one string in total, right? How much PV cells did we use in total? Well, obviously it's 96 cells because each one's 1 watt, right? So you can see the main thing I want to show here is you could change the voltage and still keep the same power, right? So it's kind of like, think of it, two levers you change. If you increase the voltage, you have to decrease the current and vice versa to keep amount of power. Conversely, if you want to increase power and keep the voltage steady, just increase the current, right? Or if you want to keep the current steady, increase the power, increase the voltage. So there's multiple ways you could figure this out at the end of the day, right? But for the most part, when you build a PV systems, you're going to be looking at the output voltage and the output watts, and then you're going to figure out how much current you need, and then we could design the rest of the system based on that. I want to talk about that next week and so on when we start building actual whole systems together. Okay. So we talked about the individual cell itself. I kind of showed you a little example of how I start building a solar panel or a PV module rather. And this is what the PV modules look like. Okay. So here, solar PV modules come in many sizes and shapes, mainly based on number one, the technology. Manufacturers have their own style. They want to, cut corners or make it nice and flashy or something, aesthetically pleasing, and also based on the voltage class and the power class, right? The more power output you want for a solar module, obviously the size has to increase. There's no way around this, okay? Just give you an idea of how tall everything is. These are your monocrystalline solar panels or PV panels. This is your polycrystalline. You could tell because it's not as solid, right? And then different versions of it. So you can see small ones, big ones, all sorts in the middle. These you can actually count how many cells they have. If you look at it, you could go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is 6 by 12 or a 72 cell panel. There's other ones a lot smaller, so this might be like a 51 or a 40 watt cell panel. So it really depends on how much power you want out of it, how much voltage. You're gonna have to buy that size from Amazon or whatever manufacturer, and there's going to be obviously you got to place on the roof, so you have to calculate how much roof space you have. These are your traditional PV modules. You have smaller individual ones. People are talking about using rooftop shingles. So instead of having to stand a little asphalt shingles, we could literally put individual cells here to where it kind of blends in the roof, so it's not aesthetically different. Obviously, these are a lot more expensive than your flat panel ones, but it's people like to hide things on their roof to make it look normal and all that. So it's just another way to get on PV panels there. Okay. So let's start talking about the PV cell characteristics of how they operate. When's the best time? What's the best operating point? What's temperature and everything else? The more details inside it. Okay. The most important characteristic of PV cell is where is the maximum point of operation. So remember, the PV cell can have up to 2 amps current limit and up to about 0.5. You can even stretch it to 0.6 volts if you really want. Somewhere within you can operate up to this. So you can always operate less than this if you want to, but you're just going to get less power. So the question is where can we get the most power out of everything? Right? Believe it or not, it's not whenever you have the most current. It's not always when you have the most voltage, right? How do you get the most current out of a solar panel? Is actually by shorting the output. If you short circuit the output, you take away any resistance, the current can go as max as it can. It typically maxes out by like 2, maybe 2.1 amps. But the problem when you short circuit, which is right here, this red dot, you have the highest current, but you have no voltage. So if you have I equals 2 amps, but you have no voltage, what's your power? Your power is going to be 0 watts because remember, power needs both voltage and current to operate correctly, right? So short circuit gives you 0 power, maximum current. You could do the opposite side where you have the maximum voltage. How do you get the highest voltage possible? You don't let any current out, right? So you open circuit the load. There's no load. So you have 0.6 volts, but your current is 0. Your power is also 0 as well. So this is not You don't ever want to operate in these two extreme ranges. You want to operate somewhere in the middle, right? And then this curve is not linear, so you're going to have to use some level of some type of iterative approach to find a maximum power point, right? We could kind of guesstimate that it's maybe around 0.5 volts at like 1.8 amps or something like this, just by this graph, okay? But we won't truly know unless we use some level of calculus or some type of iterative approach to figure it out, okay? So here's kind of a computer simulation where they plotted what's the maximum power based on your voltage times your current. So remember at the very bottom here, this is your short circuit current level where you have no voltage, so you have 0 watts. But as you build voltage and you build current, your power is going to increase. There's going to be an upper limit right here to eventually your current will start decreasing and you'll get the open circuit voltage and you're going to get 0 watts again. So just looking at this graph, somewhere about right here is your maximum power. So this is your operating point right here, right? So I'm going to guess it's probably like 1.8 amps to about maybe 0.52 volts, some close to it, right? So how do we reach a maximum power point in PV cell? When volts times current is the highest, roughly, very roughly, again, we always say it's 0.5 volts and 2 amps, right? Each individual PV cell manufacturer might have small variations based on their design, their manufacturing process, but we could usually kind of say, let's just round it off to half a volt and 2 amps, okay? When is the power output zero? Again, at short circuit current where the voltage is zero, so P time equals V times I is zero, or open circuit where no current is flowing, so you're not doing anything to the system, right? The load's disconnected. Okay, so this maximum power point is a very big deal in solar panel systems and any type of PV systems, modules, solar cells. We always want to make sure we're operating up here. Otherwise, we're just losing money, right? No one wants to spend 10,000 bucks to buy a whole solar array setup and operate all the way down here and get half of what you're supposed to get, okay? And we're going to talk later, there's all sorts of algorithms to make sure we stay at that absolute maximum power point. There's a whole industry behind it, power electronics and inverters and blah, blah, blah. All right, so what other thing is going to affect how much current can come out or how much voltage and power goes out of PV cell? You know, nothing's perfect in the world. The main thing that will affect it is the irradiance, how much sunlight is hitting us. An extremely hot sunny day, we're going to get the most direct sunlight. We're going to get the highest amount of current. In a very cloudy day, it's going to be much less. In the wintertime, it's less. Why? Because we have less sunlight. Okay. Obviously, at night, there's no sunlight or very little sunlight. Technically, there's a little bit of sunlight because it gets reflected off the moon, but it's so small that the PV cell panel is not going to really do much. Okay. So there's direct correlation to the amount of irradiance and how can we calculate, how can we quantify that? Well, remember, we get about 1,386 watts per meter square from the sunlight hitting the top of the atmosphere. As it goes through the atmosphere and reaches the Earth where we are, the hottest, sunniest days, you might get 1,000 watts per meter square. At this point, this is a perfect ideal conditions. You're going to get 2 amps. Okay, and it gets kind of cloudy. Maybe something's wrong. It's not in the summer. You might get to about 600 watts per meter square. Right, so it's less sunlight coming to you. So obviously your currents can go from 2 amps down to like 1.2, 1.15. So lower current, you're going to lose power. I mean, that happens, right? Cloudy days kind of suck for solar panels, right? And then you get all the way down to 200 watts per meter square. This is like it's straight up raining and it's dark, right? You're producing nothing. You're producing a quarter amp, so you're running at 25%, probably less than roughly like 12% efficiency, right? Which is terrible. So your solar panel's just not doing anything that day. Okay. So irradiance decreases. What happens to the current and the output? Current directly decreases based on the sunlight available, and power decreases proportionally as well. We lose half our current, we lose half our power. Okay. Why would irradiance decrease? Cloudy days. Your trees can block the sunlight. So maybe in the morning, in like 10 a.m., the way the sun hits your property, there's a tree that blocks the sunlight to the solar panel, right? So that kind of messes things up. You can have some low radiance. Right? Wintertime also, because the sun is further away from the earth. Remember, the In winter, we're kind of tilted away from the Earth, so the sunlight has more atmosphere to pierce through. It's going to lose a little bit of energy. That's why the winter is cold. Okay? Sunlight is very hot because where the sunlight is directly hitting us or as close as possible, there's less amount of atmosphere for it to go through, so we get more energy from it, and it heats up the Earth more. Okay, so that's the radiance levels. Other things could affect the PV cell operations is temperature, right? Hotter the temperature, you can get lower voltage, right? It's just the hotter the temperature, it's going to be harder for the electrons to kind of get knocked out. They want to not move as much. It's just overall bad. You know, we all know heat in general is the enemy of electrical engineering. It melts things, it makes things slower, not as efficient. So obviously, less heat, the better. So here you can see that if we have 25 degrees Celsius, we're running a little bit above our typical short circuit voltage. As temperature rises, we're going to get less and less voltage. You see at 60 degrees Celsius, that's really, really hot. That's you're going to burn your hand a little hot. You're going to get lower voltage, right? So lower voltage obviously means less power, right? So as temperature increases, bounds to the voltage and power output, voltage decreases slightly, power decreases slightly. Now, I'm going to say temperature variation changes the voltage a little bit. It's not as drastic as the sun and the irradiance and the current. So even if it's a very, very hot day, you might only lose maybe 5 or 10% of your power. It's not the biggest a deal, right? Unfortunately, it's just the way solar panels operate. They thrive the best in direct sunlight. Direct sunlight also heats the solar panels the most. So you can get the hottest temperature and the brightest day where you get to make the most power. So it's kind of like you're getting both. You're getting the best of direct sunlight. You're getting hurt a little bit because of high temperature, but you melt it together. You're still getting a net benefit out of it. Okay, so I wouldn't worry about temperature too much unless you're like putting this on an oven or something that gets way hotter than what the sun gives you, right? If you're putting this on top of like a diesel engine or something silly like that, yeah, or a boiler, yeah, you might have some issue. But as long as you put it on the roof with shingles and the only sunlight, you shouldn't have an issue. Okay, they're built for that. Okay. Why would temperature increase? Hot summer days are always get hot. I mean, that's just the rule. Okay. So that's PV cell temperatures. Other things you want to look at for a PV cell, you can buy different types and different manufacturers. We need to make sure we can depict from what's a high quality PV cell that's worth your money and a cheap piece of junk you're gonna throw away in 2 years and you're just wasting your money. Okay. So how can we compare this? Well, we can compare what the actual operating performance is versus a theoretical perfect condition. Right. The closer we are to the perfect condition, the better the quality the PV cell is. One way to do that is the actual maximum output power is that maximum power point. We talked about trying to figure out where it is, right? Figure out what that is, and then compare it to the ideal, unrealistic yet ideal conditions. Ideal conditions is where you have the absolute highest short circuit voltage multiplied by the absolute high short circuit current. That'll never happen in real life, but that's like the bar we should always try to reach. The closer we could get to this ideal theoretical output power, the better off our device is going to be. So we could do a ratio factor. It's called a fill factor, where you take the actual output divided by the ideal theoretical output. This is typically in a percentage. And then we could say, well, the closer we are to 100%, the better off we're going to be. Anything with a fill factor of 90% is considered very good. Once you get down to like 70%, that's considered junk. I wouldn't buy that. You're just wasting your money. This is a kind of little graph to show you the little gray square. This is the most idealistic version you could get, where it's basically comparing the area under the curve, right? So this gray box is the best conditions. The blue box is the actual power that we get on the normal operations. The more the blue box fills the gray box in total, the better off a panel is going to be, right? So in this case, this is a really good one. If you look over here to the right, this is a kind of not so great one, because you think about what's the ideal condition. It's going to be this square right here. But then look at this red line. This is a poor fill factor. So if we ever draw out the current, it's going to be very small, right? And we can do it real quick. Right, let's see. Let's do orange. So let's say maximum power points are right there. So if I draw my box, it'd be like this. right? This much. That's really not that good compared to this green one. So if I have a PV cell buying with this red maximum power point track curve, this is garbage. I'd return and get my money back. Okay. So fill factor is typically a quantity you're going to see when you buy a PV panel. It will say 85%, 92%, or so on, right? If they don't have it, it probably was a crappy one that you're going to calculate on your own and probably realize I shouldn't buy this because they're hiding it, right? Any manufacturer, if they're good, they're proud of their high fill factor, they will print it just to say this is a plus feature, okay? So in general, we talked about PV cells today. PV cells are mostly made out of crystalline silicon with impurities, antimony Sb and boron B. You sprinkle those in, you bake it, and then now you have a semiconductor material. Right? There's three types of PV cells we can see and use: thin film, polycrystalline, and monocrystalline. Monocrystalline typically is the best one. This is what most people buy because they want bang for your buck and longevity. Okay. PV cells typically have an electrical output of a half a volt and 2 amps, which means that their real power P is 1 watt. You can typically use that as a standard when you're counting cells and designing any type of PV module. Okay. A single cell doesn't really do much, so you want to group them together in a solar module or a PV module, right? And the idea is you want to wire them in series to make a PV string to create the voltage you need. And then after that, copy and paste that PV strings in parallel and increase the current until you have the correct power output you need. And boom, there's your solar panel. Okay. Now remember, all PV cells they're going to be affected by irradiance of how much sun is hitting it that particular day and time, the temperature of the PV cell as well, and the fill factor, which is how high of a quality the PV cell is from the manufacturer you bought. Okay. So with that being said, I think we'll call it a day today for the building block of solar panels. Right. We're going to come back next week and we're going to talk about solar modules, putting it together and kind of sizing in some basic requirements for, let's say, a household PV system on your rooftop or something like this. Okay. So with that being said, thanks for showing up and listening. Hope you guys have a good rest of the week and we'll catch you next time. See you around.